All right, now let's talk about temperature units. They're easy. They work almost like numbers. So we've seen that units and dimensions work pretty much like fractions. But what about temperature? Well, temperature is a little bit different. It's an interesting thing, and actually what I'm going to describe here is part of the ideal gas law. In fact, if you look at the picture, you'll see a tool. I can't remember the name of it right off. I should have looked that up before I started this. But we've got one in the lab, and if we were in class, I would pull it out at this point and pass it around and let you see it. It's a pretty simple device. You'll notice on the left-hand side there's a sort of a bulb. It's a sealed bulb, except for the tube that goes in the top of it. And you can put any gas into this thing that you want. You can't see it very well in this picture, but just below the gauge to the left, there's sort of a T that ties the gauge in with the bulb, and it's actually a handle in the back that allows you to hold the whole apparatus. On the front of that T, there's actually a little dark hole. You might be able to see it. That's where you can inject whatever gas. You can evacuate this thing out, evacuate that bulb and all the piping, and put whatever gas into this device that you want, and then seal it off. Now, the way you use this device is you expose the bulb to whatever temperature source you want. It could be a flame, could be an ice bath, whatever you want, doesn't matter. And you measure the pressure. Of course, you can measure the temperature of the thing you're exposing it to with a thermometer, and then you could plot pressure versus temperature, right? So if I know what temperature I'm exposing the bulb to, I can read off the pressure and plot a point on a pressure versus temperature graph. If you do that, depending on how much gas you have in the cylinder, and also depending on what type of gas that is, you'll get a different curve or a different slope. It's not a curve. If the gas is ideal, you'll have pretty much a straight line. Well, if it's completely ideal, you'll have a perfectly straight line. But gases are not perfect, but they can be close enough. And what you'll notice is you'll get a family of lines that are just straight lines and sloped at different angles. The interesting thing about these lines is that they intersect back on the horizontal axis at a pressure of 0 at a very specific point. It's always exactly the same point. Now, you can't actually take the bulb and expose it to colder and colder and colder stuff and keep measuring pressure. The problem with that is pretty much any gas I know of will actually liquefy out, right? So eventually it'll turn into a liquid. It no longer applies pressure to the pressure gauge because it's no longer in contact with the gauge. It's just liquid down in the bulb. And so you can't actually take these gases all the way down and complete these lines. But if you extrapolate them, the really fascinating thing is that they all go down to a very special point. And of course we call that point absolute zero temperature. As far as we know, you can't go any lower in temperature than that. Some interesting temperature scales we use fairly commonly. You've probably grown up with Fahrenheit, maybe Celsius or centigrade. Centigrade's sort of the older one, right? Celsius is the same thing. It's just we call it Celsius. I don't know the story behind that. There's probably one, but it's not our focus. You may have heard of the Kelvin scale. It is an absolute temperature scale that is based on the 0 point, right, that we don't think we can go down below. I know we've gotten very close to absolute zero. Don't think we've ever gone below it. That would be pretty big news. But you can see some representative temperatures here. For example, dry ice, which is solid carbon dioxide, exists at negative 108 Fahrenheit, or about negative 78 Celsius, or a balmy, 195, 200 Kelvin or so, something like that. And you can see several different example temperatures here. Some interesting temperatures that are world records, for example. Lowest temperature on record that's officially recorded was in July 1983 in Vostok, Antarctica. There's probably been a day or a place on Earth that was colder at some point, but we don't have any official temperature measurements. You might think that the world record for highest temperature has been set recently. Actually, it was set back in 1922 as far as the highest official temperature ever measured. And that was recorded in El Azizia, I believe you pronounce it, Libya, back in September of 1922. So that would be a very hot air temperature, and I'm sure that you wouldn't last in it very long. But there's some interesting record temperatures. So I claim that temperature units are easy. They work almost like numbers, but we need to think about them a little more deeply. You've probably heard of the Kelvin scale along with the Celsius scale, and you probably know that the Kelvin scale begins at absolute zero, and the Celsius scale has its zero at the freezing point of water. I want to give you a visual that might help you with that. I'm going to put up two different rulers. One, the upper ruler represents the Celsius scale, and the lower ruler represents the Kelvin scale, and we'll just use the centimeters or the metric portion of these two scales right now. Now think about converting between these two scales. If you have a temperature in degrees Celsius and you want to get that temperature in Kelvin, you have to add 273.15 to the temperature in Celsius. Now you need to commit that 273 to memory, but don't worry about the 0.15. It'll be very rare in this course that we care about that level of precision. The 0.15, you can just remember that the difference between the Celsius and the Kelvin scale is 273. Okay, so the freezing point of water, of course, is 0 degrees Celsius, and it's 273 or so Kelvin. So this is a lot like two rulers that are offset from each other, so that the 0 point of one scale corresponds to a non-zero point on the other scale. So you see up here, I'm by analogy using the 0 centimeter or millimeter line down to the 2.5 centimeter or 25 millimeter line on the lower scale. That's analogous to what we're doing here. Okay, so you just need to remember the offset between those two scales is 273 degrees. What about temperature differences? You see, there are temperatures and then there are temperature differences. As a matter of fact, the temperatures we've dealt with so far, there are two different types, right? There's the relative scale of Celsius and the absolute scale of Kelvin. Those are very different things. And depending on what your equation calls for, you've got to use the right one. If you use the wrong one, your equation won't work. So already we see there's a difference between absolute and relative scales. You probably already know that, but here's something you may not have thought about. How much difference in temperature is there between the boiling point and freezing point on the Celsius scale? Well, let's see. Boiling point's at 100 Celsius, freezing 0, no problem, that's 100. What about on the Kelvin scale? Well, actually it's exactly the same amount, because on the Kelvin scale, the boiling point of water is 373.15, the freezing point is 273.15. The difference between those two is 100 units difference. Now, on the Kelvin scale, we don't say degrees. We don't say degrees Kelvin, we just say Kelvin. So there's 100 Kelvin difference between the freezing and boiling point of water on the Kelvin scale, just as there are 100 degrees difference on the Celsius scale. This is analogous, again, to the two rulers being offset and measuring the difference between two positions, two distances, right? So on the upper ruler, this would be like the Celsius scale, and you can see the distance between 1 and 3 centimeters is 2 centimeters, right? Well, if we pull those lines down to the analogy for the Kelvin scale on the lower ruler, then we're at 3.5 centimeters up to 5.5 centimeters. Again, that difference is 2 centimeters. So you have to know whether the equation you're working with calls for absolute temperature, relative temperature, or a temperature difference. And to me, the big one is the temperature difference. Most of the time you can get away with just sticking with absolute units, but when you need a temperature difference in an equation, you have to think a little bit differently. Okay? What about between Rankin and Fahrenheit, or degrees Fahrenheit? Now, you may not have heard of the Rankin scale. It's kind of like the answer to the absolute temperature units in SI. It is the absolute temperature unit in English units. So it begins at absolute 0, just as the Kelvin scale does. And so, again, this is just like two rulers that are offset from one another. The Fahrenheit scale is above, and the Rankin scale is below. In a similar way, one particular measure, one particular temperature on the Fahrenheit scale corresponds to a different number that is just offset on the Rankin scale. So that difference is 459.67. Again, we usually don't need that much precision. So just in your mind, you might want to write this down. As we have 273 difference in Kelvin and Celsius, between Rankin and Fahrenheit, we have about 460. Now, that's not exact. Obviously, it's a little less, but it rounds to 460, and that's close enough for what we're doing. So I want you to remember that the difference between Fahrenheit and Rankin is 460 degrees, okay? So if you have a temperature in Fahrenheit, simply add 460 to it, and you will get pretty close to the temperature in Rankin. So 32 degrees Fahrenheit, which is the reference, the freezing point of water, of fresh water. If we add 460 to that, we'd get 492, which, of course, I've got the right number here, but that's the temperature in Rankin, roughly, of the freezing point of water. In the same way, on the rulers, you see 3/8 of an inch corresponds to 1 3/8 of an inch on the lower ruler, because there's a 1 inch offset between the starting point of the two rulers. That's all that's going on here between the Fahrenheit and Rankin scale. Now, how about differences? Well, you know that the freezing point of water is 32 degrees, the boiling point is 212, if we're talking Fahrenheit. In Rankin, that is 492 to 472. The difference between those two are both 180 degrees, right? Again, on the Rankin scale, just like on the Kelvin scale, we don't say degrees Rankin, we just say Rankin, okay? But on the Fahrenheit scale, we can say degrees Fahrenheit. So 180 degrees Fahrenheit is the difference between the freezing and boiling point of water, or 180 Rankin is the difference between the freezing and boiling points of water as well. So if we're looking at temperature differences, well then again we're measuring the distance between two things. So let's use our ruler analogy again. So you notice that the left line is on about 3/8 of an inch on the upper ruler, and it's on about what, 1 1/8 inch. The difference between those two is about 3/4 of an inch. Well, looking at the lower scale, the first line is on 1 3/8, the second line is on 2 1/8. Again, the difference, if you count it, is what, 1 2 3 4 5 6 eighths, or in other words 3/4 of an inch. It's the same difference on the two scales because the two scales have the same unit size, you see. Now obviously centimeters and inches do not have the same unit size. 1 centimeter is a lot more distance than an eighth of an inch, for example, or you could say a millimeter is a lot, well not a lot, but a little bit less distance than 1/16 of an inch, for example. In the same way, Fahrenheit and Celsius have different sizes. So that's why in this equation that you see, that you've probably learned by now, maybe you've committed it to memory. I don't know about you, I always struggle to remember it, but I've got it right here for you. When you convert from Celsius to Fahrenheit, there are two things you have to do. Let me show you using the ruler analogy. So the upper ruler is going to represent Celsius, so we use the metric, the millimeters or centimeter scale. And then the lower ruler will use the inches scale. So we'll do all this by analogy. So if we're interested in converting from one number on one scale, the millimeter scale, to a length on the, or a position on the inch scale, understand that these two have an offset, right? Their zeros don't start at the same place. The 0 point, the freezing point of water, is the 0.4 Celsius, but 32 degrees is the freezing point of water on the Fahrenheit scale. Therefore, the 0 for the Fahrenheit scale is somewhere below the freezing temperature of water. So we've got that offset between the two rulers. So that's one thing that has to be taken care of. That's why we've got 32. That's the bias or the offset in the equation. But then the unit sizes are different, right? A millimeter and an eighth of an inch are two different unit sizes, or you could say a centimeter and an inch are two different sizes. Okay, they're two different amounts of distance. In the same way, 1 degree Fahrenheit change is different than 1 Celsius change. That's why we have the 1.8 multiplier. Because you see, if the temperature outside were to go up by 1 degree Celsius, it would go up farther than 1 degree Fahrenheit. In fact, it would go up 1.8 degrees Fahrenheit. That would be the increase, okay? So in our particular case, since we have the offset 0, we're trying to convert 6.5 centimeters over to the inch scale, and it comes out somewhere above 3.5 inches. And the reason is because there's two of them. There's an offset on the 0, and there is a unit size difference. So that's analogous to the Fahrenheit and Celsius conversion. What about changes in Fahrenheit and Celsius? Well, in that case, we don't need the offset, right? Because in that case, we don't really care where the zeros are of the two scales. All we care about is the distance between 2 points on those two scales. So you'll notice I've drawn two lines here. The one on the left is at 1 centimeter. The one on the right is at 3 centimeters again, so that's a difference of 2 centimeters. On the English scale, that's about, well, let's see, we're at about 1 3/8 inches, and then the right is somewhere a little bit north of 2 1/8. So the difference between those two is, again, I think 6. 1, 2, 3, 4, 5. Yeah, 6/8 or so, a little more. And so a little more than 3/4 of an inch is equivalent to 2 centimeters, you see. And if you grab your calculator and try the conversion factor, you may know, you'll see that this is true. So the conversion factor, by the way, is 2.54 centimeters per inch, and you can see that this works. So similarly, on a Fahrenheit and Celsius difference scale conversion, you have to take the change in temperature in degrees Celsius and just multiply it by 1.8. You do not add 32 to this because you're interested in the difference between two temperatures on this scale. And of course that bias, that offset, just cancels in these two. What about Rankin and Fahrenheit? Well, here's a conversion you may or may not have learned already. In this case, both rulers start at the same point, right? They both have their 0 at absolute 0, but their unit sizes are different. So again, we have to multiply 1.8 by the Kelvin number in order to get Rankin. So if we want to convert 0 Rankin to 0 Kelvin, no problem, right? They're the same thing. But if you wanted to convert, say, 5, I'm sorry, let me go according to what I've got here on the slides. If you want to convert 2 inches to the same position on the metric scale, then you're at 5 centimeters. Sorry, I flipped the rulers on you that time. Which is about right? I mean, 2.54 centimeters per inch, yeah, roughly 2 inches would be about 5 centimeters. In the same way, if you want to go to Rankin from Kelvin, you multiply the Kelvin by 1.8 and you're there. How about differences? Well, the equation here looks just like the one on the last slide, but now we're converting two different, or a range of temperatures from one scale to the other. And so we're interested, even though the two scales begin at the same 0 point, now we're talking about a difference between 2 points, and if there were any offset, it would cancel anyway. So same thing that we've seen before. So here's your first question. Now that you understand there are 3 different temperatures, there's relative, absolute, and temperature differences, which one does the ideal gas call for, or the ideal gas law call for? You may want to pause this video and think about it for a minute. Now that you've paused the video for a moment, or maybe not, maybe you just kept watching, the correct answer is absolute temperature. That's the one that you have to use in the ideal gas law. If you put a temperature difference, or you put a relative temperature, say in Celsius or Fahrenheit, the ideal gas law tells you nothing. One interesting thing is you have to also have absolute pressure in the ideal gas law for it to work for you. So just something to know. We will use the ideal gas law later. We'll talk about it more because it doesn't always work, and we'll have ways of correcting it.